So who's a good nucleophile? Who's a good electrophile? Carbonyl is our electrophile.
The nitrogen's a good nucleophile.
Nitrogen's a good nucleophile with its lone pair. Okay. Anybody have an idea how we might start this mechanism? There's a partial credit start point, and then there's a full credit start point. Let's see which one you grab. What's that?
Protonation.
Protonation, that's the full credit answer. Protonation of what with what?
The oxygen with the hydrogen.
Good. So lone pairs on the aldehyde, HCl. We protonate the carbonyl group. Now why did you do that? It's right, but why did you decide to do that?
Because it says catalyst.
Okay. Well, it helps the reaction, yeah. So the HCl would need to be involved in some way along the mechanism. But why not just make the amine directly attack the carbonyl group?
Does it make the carbon more positive?
Yes. Protonation here makes the carbonyl group much more electrophilic. So we protonate the carbonyl oxygen. And now we have an intermediate that has resonance. So now our carbonyl group is a much better electrophile, much more willing to pick up a proton. Remember we said that in class yesterday, that the acid derivatives, under acid conditions, we protonate the carbonyl group. Same thing here. A carbonyl group under acidic conditions, the carbonyl group is going to get protonated, and that's going to make it a better electrophile. Okay, so we're good on that one. These are resonance structures. All right, what's next?
The nucleophile attacks.
Nucleophile attacks. So we've got our amine. I'm going to abbreviate the CH2CH3 group with ET, just to make it shorthand for ethyl. So our nitrogen lone pair attacks our carbonyl carbon, and we push electrons up to the oxygen. Is that all right? Are we good?
There's a plus charge on the nitrogen.
Yes, there's a positive charge on the nitrogen. Everybody good up to that point? Okay, what's next?
The oxygen pulls out the nitrogen from the nitrogen.
So this is this going to be a good leaving group just to fall off by itself? Now when it falls off, it will be hydroxide, which is a strong base. Strong bases are bad leaving groups. It would be better to put a proton on it. We could take a proton from HCl if we wanted, but we've also got a proton right next door here on the nitrogen. So a much easier way is just to say steal hydrogen from nitrogen. So we had an internal acid-base reaction. The OH group stole a proton. Okay, everybody okay to that point? All right, what's going to be next in the mechanism now?
The water goes away.
Water goes away, it's a good leaving group.
And the lone pair forms the carbon-nitrogen double bond.
Lone pair of the nitrogen comes down to make a carbon-nitrogen double bond. Yes, both of those things happen. Looking okay? You sure?
Sure.
Charge on nitrogen. Keep making that mistake for a reason. Okay, now what happens next?
The seal from the beginning.
It could. We also lost a water molecule right here. So you could either use the Cl- from your starting material, or you could use your water molecule as a base. I'd accept either one of those. Water is probably a more realistic base, because what happens when you put HCl into water? Well, the HCl gives up its proton to water, so it's a strong acid. So our water molecule comes in, pulls off the proton, and now we've formed an imine. So you can see it's a similar length of mechanism. It's almost like the acid derivatives. This is a little bit longer of a mechanism than the hemiacetal acetal hydrolysis. Okay, are you okay on mechanism, you think, with those two examples? For those of